All right, so today we're gonna jump into capacitors. Capacitors are a cool thing. Sorry, my thing is going crazy. Capacitors are a cool thing. So if I put two parallel conducting plates, we create a thing that's called a parallel plate capacitor. And so if you're into electronics and you talk about capacitors, this is what capacitors are based upon. And as we start to see the relationship between the charge, the voltage, and capacitance, it'll start to make sense. So basically, it's easy to see the relationship between the voltage and the stored charge of a parallel plate capacitor. Each electric field starts on the positively charged plate and it ends up on the negatively charged plate. So there'll be more field lines if there's more charge, right? So if I have so in other words, these little plus lines represent the magnitude of the charge, right? And so if I have more charge, the more electric field lines I have, okay? And each electric field line starts from a positive charge, jumps across to the negative charge, again on the ends. We get a little wonky, but most of the time they're uniform and straight, except for the two on the ends, right? And the electric field is actually, and we're going to start to talk about this today, the electric field is proportional. That little symbol, the alpha, when we write it in this way, means proportional. Oops. To our charge, okay? So it's directly proportional to our charge, right? And so that means we're going to recall some things. Remember that your voltage is equal to the electric field times the distance between the plates, right? Between the charges. So then that means that V is directly proportional to the electric field, right? And if that's the case, then that means that V is directly proportional to the charge Q, or I should actually write this the other way. Q is directly proportional to voltage, right? So our charge is directly proportional to our voltage. So this is true in general. The greater the voltage applied to any capacitor, the greater the storage it'll have. And so one way to measure that is we define this as capacitance. So C, capital C, doesn't mean Coulomb in this case. It actually means capacitance. And we quantify that by saying that the charge is equal to the capacitance times the voltage. And that's just, kind of working our way through there. Okay. Now, this equation, the two major factors affecting the amount of charge that's stored, right? So voltage and charge are connected to capacitance. Now, if I take that same equation and I solve for capacitance, I see that my capacitance is actually equal to, I hate when this does this. My capacitance is actually equal to my charge divided by my potential. And so this is how we measure, in other words, if we go back here and we look at this, if I have more voltage, that means I'm going to have a greater charge, and vice versa, right? We know that, right? So then the electric fields will be more abundant. We'll have more electric fields. And then we're trying to measure that. And so one way we do that is we actually take the charge and divide it by the voltage, and that gives us our capacitance. And so this is going to be charge per volt, right? So we could say Coulomb per volt. So now this would be Coulomb. I always misspell his name. I'll probably misspelled that. Per volt. Okay. And capacitance was actually Michael Faraday is the guy that kind of came up with this. I did spell his name wrong. I knew there was a U. I always put it in the wrong spot. So technically this is an O. Oh, no, this isn't working. And there's a little U right here. We'll just erase it. And so 1 Faraday is equal to 1 Coulomb per 1 volt. And so this is named after Michael Faraday. He was the guy that was like, hey, we need to measure this. Okay. And we know that they're proportional, and so he derived it, and he said, well, I'm just going to measure it this way. Okay. And then the most, and I do want to remind you of this, if you see this P Faraday, that's pico. I hate this towards the end of the video. My computer always acts up. So this is pico. That's 10 to the negative 12, if I remember correctly. And then you guys know what milli is, right? That's just milli. That's 10 to the negative 3. Okay. And so where are we going with all this? Well, this let me show you what modern day capacitors are like. So we kind of take those things and we put them in something like this. So here are some images of some different modern day capacitors. And so capacitors are nice because we can capacitors kind of when you have a real electronics, it pulls voltage. So like, for example, I'm one of the robotics coaches. So when we build a robot, when a motor turns on, it pulls some voltage. That changes the overall potential on the system. But we still want to have voltage to do other things. So we might run 4 or 5 different motors. Sometimes we turn all 4 motors on at once, and then sometimes we only turn on 2 or 3. So we have capacitors in our controllers that actually kind of charge and maintain that potential. So it pulls the potential from the capacitors, and then once it's done that, for that quick little spike, then the capacitor itself kind of recharges. So you can think of this like little mini batteries that discharge quickly. And so, I mean, that's basically it. And so then there's a little bit more math, like how do you design these? So essentially you want, what the heck is going on? You want to like have calculations. You want the capacitor to hold a certain amount of charge. Usually we measure that. You can measure it based on the capacitance, which is in Faraday. But to calculate the Faraday, you really need to know like the separation of the plates, because that has an impact on the electric field, and the voltage of the battery. What is the source of the voltage usually? So parallel plate capacitor with plates separated by a distance d, we end up with this equation where we can calculate the capacitance is equal to this value, which is it's epsilon naught And we just call this the permittivity of, why is this not working? So this is epsilon sub 0. I'll explain that in a second. Times the cross sectional, the area of the plate divided by the distance between the plates. And so E is our permittivity of free space, right? Shoot, why is it not? So by definition, we call this the permittivity but it's really just a scalar multiplier. And this has a value, so it's a constant. That value is 8.85 times 10 to the negative 12. Or wait, I gotta remember, is it negative 12 or positive 12? Yeah, it's negative 12. And that is in Faraday. Very frustrating when my computer does that. Faradays per meter, right? And then that'll cancel out with the meters, and that leaves us our capacitance and Faradays, okay? And so obviously we're going to do some math on this today. So let's do an example of this. All right, here we go. What is the capacitance of a parallel plate capacitor of metal plates? And they give us the area, and then they give us the distance. What is the charge that will be stored? And what is, okay, so we got a lot of stuff to do. We got A and B. So remember, the first thing we could probably calculate, remember that the capacitance is just going to be the permittivity of free space times the area divided by the distance. And then also to find the charge, we just take that capacitance times the voltage. So let's see what they give us. They give us the area. That's 1 meter squared. They give us the distance. That should probably be in meters too. So it's 1 millimeter, so it's 0.001 meter. Permittivity we know, oh, and the voltage. So the voltage is equal to 3.00 times 10 to the third volts. So the first thing I want to do is I want to calculate the capacitance. So the capacitance is equal to this 8.85 times 10 to the negative 12, right? Times the area, which is 1, divided by 0.0, oh, that's going to be a big number, 0.01. And then that gives us, I think it's 8.85 nano Faraday. Okay. okay? Because I think it's 10 to the negative 9, because you have, this is 10 to the negative 3, that goes up on the top. You know, you add 3 to this, so it'd be negative 9. Okay, so then now that we know the capacitance, so that's kind of part A, easy peasy. And so then to find the charge, we're just going to take the capacitance, which we now know is 8.85. It's nanofarad, so I'm just going to say times 10 to the negative 9 Faraday times, remember this is the capacitance times the voltage. This would be 3 times 0 times 10 to the third volts. That's a V. So my charge then ends up being 26.6 times 10 to the negative 6 coulombs, or 26.6 microcoulombs. And that's basically it. So you hear this term a lot, and I don't know if I'm gonna, I wish I had an image. The textbook explains kind of a dielectric. So I'm definitely going to write down let me explain. So in terms of biology, electric potential is found in our cell's plasma membrane. The membrane basically sets the cell off from its surroundings and also holds ions to selectively pass in and out of the cell. Now, if you remember, ions are just positively or negatively charged molecules based on their number of electrons they have. If they have an extra electron that they're not supposed to have, then they have a negative charge. If they're missing an electron that they're supposed to have, then they hold a positive charge. And so there is a potential difference across the membrane. So they have a potential difference of about negative 70. Oh, I've got to hurry up and finish this video. It's really getting on my nerves. All right, let's try this again. Negative 70 millivolts. Okay. And this is due mainly to negatively charged ions, but specifically sodium. The negatively charged ions in the cell and the predominance of positively charged sodium ions. So remember that sodium that's what salt is. It's sodium chloride, but the chlorine has a negative charge and the sodium has a positive charge. Okay, and so this is on the outside of the cell, so it pulls the negative charges to the perimeter. So things change in the nerve cells is stimulated. So the sodium ions are allowed to pass through the membrane into the cell, producing positively charged membrane and a nerve signal. The cell membrane is about, the thickness of the cell membrane is about 7 to 10 nanometers thick. And so if we wanted to calculate the electric field, remember that the electric field is equal to the voltage divided by the distance. So that would be negative 70 times 10 to the negative 3 volts divided by, we'll just go in the middle and say 8 times 10 to the negative 9 meters. And so then what we have on the top here is we have an electric field of about -9 times 10 to the 6th volts per meter. Okay, so an electric field is enough to cause, or this type of electric field is enough to cause a breakdown in the air. So if you have air, it's, it'll break it down. So what does this have to do with anything? Well, the difficulty of storing large amounts of charges and capacitors can be d, right? Like the distance. If you make d smaller than the distance between the plates, then you have a larger capacitance. Then the maximum voltage must be reduced proportionally to avoid this type of breakdown. So it's an important solution to this difficulty is to put an insulating material called a dielectric. A dielectric, let's just write that down real quick because I want you to understand. A dielectric is an insulator. Because if you just did air, right, the air would break down. So you have to have something in between the plates that would allow for the distance d to be close together, almost a small part, but you don't want the air, they can't touch. So, but you could still pass these electric fields through the insulator, so to speak. So not only does the smaller distance make the capacitance greater, but many insulators can withstand greater electric fields than air can before breaking down. So sometimes, and I want to point this out, we represent this with a funny, kids always call it the funny letter K, and I don't care if you call it that. There's another one, K, which is the dielectric factor, right? So this K, we've had a lot of Ks, is a dielectric factor. So it's just a number. The materials, we measure the materials to figure out what their dielectric factor is, and it has an impact on the capacitance. So if you wanted to calculate the capacitance of a capacitor with a dielectric, then you would use this formula, which is slightly different. You would have K epsilon naught times the area over. Oh, that is so frustrating. I'm almost done with these notes. Times the area over the distance, right? And then I'm going to give you a table here. There's a table. Can I copy the table? No. I'm going to paste like some things here, and this is in the book, but here are some dielectric strengths and their constants. Okay, and so this would be the value for K. That's actually the Greek letter kappa. I probably should have mentioned that. But there's just a couple. There's a complete list in the textbook. You'll probably need to look some of these up. So when you put that in to the formula, that's how you determine the actual capacitance at different, and these are constants at around room temperature. So these are the numbers you would use at around room temperature. If you have a capacitor that goes below room temperature or real above a room temperature, these would change slightly. On the dielectric strength, it's the maximum field. So these fields are basically which the material breaks down and conducts, right? So remember, like, so you have this electric field that equals the voltage divided by the distance between them. And so we have this is the maximum, the dielectric strength would be the maximum max electric field you could have. Okay? So, they give an example in the textbook. You could just read it. It's about Teflon. So, well, so the max you would have would be like, if you have paper, it's 16 times 106 volts per meter sort of situation. So let's talk about Teflon. Let's do one with Teflon. So the textbook, and I'm surprised I have this in a different thing. So they're talking about Teflon in the example in the textbook. So consider Teflon. If I look this up, Teflon, its max strength is 60 times 10 to the 6. So if I were to say Teflon right here, over here you would have 60 times 10 to the 6. I said 106 earlier. So this is actually 10 to the 6. It just copied funny. This is 10 to the 6. This is 10 to the 6. You'll see the right stuff is in the book. All right. And then what if I have the limit for my separation? So that means Teflon is about 60,000 volts, right? And then what if I have a separation of D is equal to 1 millimeter, right? So how do I figure out the charge for Teflon? One other thing I should point out is that Teflon's kappa value is 2.1. And so to figure out this charge for Teflon, I'm just going to say the charge, Q, would be kappa epsilon, or no. I got to figure out, there's still air in there, so the capacitance for air, right, which we know from earlier, times the voltage. So let me read exactly how it's worded. So it says Teflon has a greater capacitance and can be subject to greater voltage using capacitors that we calculate in the above example for air-filled parallel plate capacitor, and we find a Teflon-filled capacitor can store the maximum charge of, right? So it's going to have air, but it also has Teflon, right? So if I do air, in other words, we're gonna calculate air and compare it to Teflon. So I have this 2.1, and then we said earlier the capacitance for air was 8. That doesn't look like a parentheses. So that's my kappa for Teflon. And then the capacitance for air, which is 8.85 nanofaraday. We calculated that earlier. And then we calculate the voltage, which is actually 60 times 10 to the 4. Because I forgot to mention this. Somewhere in the textbook. Let me double. Oh, it's so if I do 6, somewhere the math is wrong. I wrote something down wrong. Let me just double check the textbook. Something didn't copyright. So 60 times 10 to the 6. If I put that in scientific notation, there might be an error in the textbook. I'm not sure if this is right or not, but in the example, they say that it's 60,000 volts. 60, no, that's not incorrect, because the textbook says that's, so let's figure this part out. So it says that, it just tells you that the maximum volts that you can use on this capacitor. Okay. So there's two parts to this. This is the dielectric strength, and this is volts per meter. And then in the textbook it says that for this design, the maximum voltage you can apply is 60,000 volts, which is important because when we get down here, we're going to get to, this is 6, it's actually 6.0 times 10 to the 4th volts, which I think is your 60,000, volts. So then it actually equates to 1.1 micro or millicoulombs. Right? And so this is 40 times the charge of the same air capacitor. Okay? Oh, I skipped the first part. So in the textbook, they said that the first part, if you built one with just air, the voltage limit would be much less. It'd be about, it'd be much less, and the charge would be much less too if you did the math on the air. So, so this would be, so Teflon. Essentially, what's going on? Teflon is allows 42 times greater charge. Oh, this is very frustrating. We're almost done. I want to go over one other thing. This is a 2, by the way. So I'm going to have two images here. I'm going to try to explain both of them. So in image A, the first one here, the molecules of the insulating material between the plates of the capacitor are polarized by the charged plates. Okay? And essentially, you have a material, and the negative charges are going to be attracted to the positive plate, and the positive charges are going to be attracted to the negative plate and also the other negative charges. So all the molecules are polarized in this dielectric, okay? And this produces a layer of opposite charge on the surface of the dielectric that attracts more charge on the plate, increasing its capacitance. The dielectric, so that's that scenario. And so when you look at figure B, essentially the dielectric reduces the electric field strength inside of the capacitor, resulting in a smaller voltage between the plates for the same charge. The capacitor stores the same charge for a smaller voltage, implying that a larger capacitor, it's implying that it has a larger capacitance because of the dielectric. Another way to understand dielectric increased capacitance is to consider the effect on an electric field in a capacitor. So when we look at figure B, okay, it shows the electric fields with the dielectric in place. Since the field lines end on the charges in the dielectric, there are fewer of them going from one side of the capacitor to the other because of the dielectric. And so since the field lines end on the charges of the dielectric, there are fewer of them going through, so the electric field strength is less. If it were in a vacuum, if there was a vacuum between the plates, even though you have the same charges on the plates, so the voltage between the plates, V equals ED, is too reduced by the dielectric. Thus, a smaller voltage V for the same charge Q, since C equals VC. So the capacitance is greater, right? So the dielectric constant is generally defined by kappa, and so this is where they derive this kappa from. So kappa is actually equal to, oh, I waited all this time. The initial electric field divided by the electric field with dielectric material, right? So I think I said that backwards, but you know what I mean. And so let's do one more. I'm going to go over one more image with you guys. Trying to hurry to get all this stuff done. And so in this image, what we're looking at this is kind of an artist's conception of a polarized atom, right? So this is like unpolarized. Like if you look at the first one, we say it's unpolarized because there's an even distribution, right? And so theoretically, you have electrons that are negatively charged. They operate in a kind of an orbital around the nucleus, which is mostly protons that have a positive charge. Polarized means that the electrons spend a little bit more time with an external positive charge and kind of avoid an external negative charge. So here we have a negative charge that's outside of the atom, and over here we have a positive charge. And so it's considered to be polarized because this is more negative because we have more negative charges on this side, and this is more positive because we have more positive charges on this side. So when we say a polarized atom, this is kind of what's going on more often than not. the electrons are still orbiting around, they're still in motion. They just spend a little more time over here because they're attractive. So they're also kind of pushed in this direction because of the attraction to the positive charge and the repelling of the negative charge. So it's almost like, and this is how planets actually orbit the sun, sort of. But it's not the same concept. So that's basically it. When you look at water, H2O is highly polarized, and we can do this mathematically. You have your oxygen and you have your hydrogen. So in this water molecule, you could see that the water is a polarized molecule where the electrons in the molecule are attracted to the oxygen nucleus, right? Because it has way more positive charges there. So that doesn't mean they don't get shared. These electrons rotate around, but there are way more positive charges here, so the electrons are kind of drawn in there. And then because of the position of these two protons, this is a proton from the hydrogen atom and a proton from the hydrogen atom, and these two can't touch. That's why we have this very specific angle. This hydrogen atom, if it's kind of polarized, mostly positive, and this is mostly positive, they're not going anywhere near each other. And so basically this is what we think goes on the inside. And so when you think of a water molecule, it's polarized. This side of the water molecule is more positive most of the time than this side, and this side is a little more negative. And it's just what happens. So I'm going to go over one little thing on capacitors, and then we will call it a day. So let me pull this up real quick. I like these visuals because they're helpful to see how things change in real time. So give me 1 second. So all electronics is a manipulation of charges and the electric fields that they create, and that has an impact on the voltage. And we manipulate all these things basically to keep track of things. So cell phones and computers, they basically keep track of charges and count the charges and manipulate the charges however they see fit. So I wanted to do capacitors. I just want the simple capacitor one. Well, yeah, we'll just do this simple. This is a precursor. I gotta hurry. All right, so let's take a look at this bad boy. So here we have a battery, and here we have two plates, all right? And here we have a voltmeter, and we're gonna see these electric fields, right? So I'm gonna put, maybe we put this here, maybe we put this here, and we increase the charge. So when I increase the voltage, right, here is the capacitance. It's 0.3 picofaraday, right? If I look at the top plate charge, it's 0.15 picocoulombs, right? If I look at the energy stored, it's 0.14 joules. The voltage potential is still there though, right? Actually, well, what happens if we do this? Uh-oh, I'm not going to tell you what that is. I'm going to disconnect this. All right. Now, if I change the separation or the size, in other words, if I increase the size, what do you notice about the capacitance? And this all relates to those equations that you guys have written down. If I decrease the separation, what happens to the capacitance? Also notice the energy stored. So there isn't a lot of energy stored here. There is here. And then the other thing is, what happens if I increase the voltage? Okay, so all of these are based on those equations that you wrote down. So I just wanted you to see that in real time. So if I wanted to store energy in a capacitor that could be used somewhere later on down the road, and when we start to do circuits, you'll see what that means. So if I disconnect that from the battery, now that that energy is stored, if I go up here and I come down here and I touch those, if I can, oh, it's not going to let me. Why isn't it letting me do that? Okay, so I have 1.5 volts stored in the capacitor. And so if I'm operating and it's completely disconnected from the battery, so you're like making a battery because what you've done is you've used the electricity to charge this plate and consequently charge this plate. So this has potential across here. Okay, does that make sense? And if I change this operation, the charge is different. If I reconnect these, and I move this back over here, and I can't charge the plate anymore. But when we start to do circuits, this will make more sense. Anyways, I'm going to stop the video here.